Okay, so this is going to be our engineered cycle. So we have a new device called a latch. And so you can just sort of see the behavior here. So when, the behavior is that when G is high, if I change D up here, propagation delay later, that shows up on Q. If I change D up here from V1 to V2, then after a propagation delay, that output, the propagation delay of the latch, the Q output will reflect that. And now G goes low, and so G is another input. We're a little worried about if I change G here, do I have to worry about the Q output? So if I change G, in sort of the most general case, we'd expect Q to sort of go bonkers. In other words, it's allowed to do anything it wants, okay, until the propagation delay, in which case it has to come up with a final stable digital value. But notice we're relying on this guy to sort of try to remember, and it would be bad for our memory to suddenly go, oh, you know, right as we say, okay, I want you to start remembering, and it goes, oh, I've forgotten. I'm in a positive feedback loop, but meanwhile, in the transition to getting into the positive feedback loop, I've forgotten everything. So we have to think a little bit about that, and we're going to dip back into our bag of tricks and think about using a lenient multiplexer, one that so long that the D and the Q inputs here are enough to determine the output value, G can change without corrupting the output. We're going to try to put ourselves in a situation where we don't have this contamination problem where we suddenly forget everything. So we're going to use a lenient mux. And a lenient mux has the behavior, well, there's sort of a couple modes here. Here's a schematic diagram for a lenient latch. So we're in a mode here where if G is 1 and D is stable for long enough, so the two inputs are now have both been stable now for TPD, we can expect Q to be valid and be stable after a TPD. So a TPD after D changes, assuming G is not changing, we're all set. Okay, so that's good. We can be in a situation now where if D and Q are both stable, so look on the graph here and find times when D and Q both have the same value. At this point, we're sort of saying, look, it doesn't really matter whether you're selecting the top input or the bottom input on this multiplexer with the feedback path, because they're both the same value. So D and Q prime here have the same value. Okay, and now G can change without corrupting anything. So that's what it would mean. That would be true if this was a lenient implementation of a latch. And in fact, we showed you the schematic diagram of that in a previous lecture. Now we're in a situation that we can, once G is safely low, once G is low and Q has remained stable, now the D input can change without any problem. And now we're in memory mode. Once we've gone in here, the information is now held in the internal feedback loop, and Q will remain stable as long as G is low. Everybody sort of happy? Are there questions about this sort of transition from loading it up to going into this positive feedback loop mode, and that by using a lenient multiplexer here in our latch circuit, we've avoided the problem of it suddenly, forgetting everything? We're relying on this sort of middle region here. When both D and Q prime, or Q, are stable, we can change G without the output changing. That's what it would mean for the latch to be lenient, that mux to be lenient. It's sort of a key thing, right? We've had to do some careful engineering to make this happen, but having done the careful engineering, we can safely let this cycle in our circuit do its job, which is to be our memory. Okay, so does this guarantee a working latch? Have we taken care of all the problems? Have we dealt with all the possible situations of D changing and G changing? And the answer is almost. Okay, we're going to have to introduce a new set of rules that takes care of one more situation. And that's the situation, what would happen if D and G, the data input and the gate input, changed at the same time? In particular, we're worrying about when G goes from high to low. we're worried about, so we're in a situation here. So here's the G signal going from high to low. So here we're in, the gate is open, and here's the gate is closed. What would happen if D decided to change about the same time? In other words, we're not quite sure what we're asking the device to remember. Are we asking the device to remember this value or that value? There are some places in here where if D changes, maybe just a little before, it's not clear whether we want the device to, what we want the device to remember. And our timing analysis on the previous page sort of suggests that we don't want D to be changing, okay, while G changes. So we're going to have to introduce another set of rules for this particular latch device, okay, that is another discipline that we're going to have to follow, something we call the dynamic discipline. So here's how those rules work. When the G is open, at some point, we're going to change the value of D, okay, and that's okay. We're allowed to wiggle D all we want when the gate is open on the latch. We're setting up this new value. And after TPD, we know that the change in D has been reflected in the value of the Q signal. In other words, that information is propagated through the latch. Okay. If we wait for another TPD, okay, we know, so that means that the Q signal has now become stable right after the end of the first TPD, because that's when Q became stable. So the Q prime input, which is just Q, has now become stable. If we wait for another TPD, now the value of Q on the output reflects the fact that both Q prime and D have the same value. And now it's safe to change G. So if we have this discipline that D has to wait, has to be stable for 2 times TPD before G can change, we're in a situation where our lenient mux is guaranteed to work correctly. And so we're going to give a special name to this delay between the last change of last change of D, of the D input, and when the G is allowed to change. And that's called the setup time. In other words, the D input has to be stable for a certain amount of time before we switch from the latch being open to the latch being closed. Yes, sir?
Why do we need 2 TPD? Because by after 1, we know that Q is stable.
We know that Q is stable and that it reflects the current D input. What we don't know is whether the information that Q prime is also stable has propagated all the way through the internal circuitry. And with our very simple timing model, we have to wait for another TPD for every node, everything that's inside of the circuit to know that these are both now at the same value, D and Q prime. Once that's true, then we can use the lenience property of the mux to actually change the G signal without worrying about corrupting the output. Does that make sense? So that's why we have to wait that second TPD. Now, in fact, in many electrical circuits, you can actually wait a little less than that. And you'll discover that if you actually pick up a data sheet for a latch and read about the various timing constraints, that the setup time is often less than twice the propagation delay. But for our very simple timing analysis, this is sort of all the best we can do given the knowledge we have. The only thing we know about the timing is the TPD timing. Okay. Similarly, we have to wait, once G goes low, we have to wait for the G going low information to propagate all the way through the circuit before D would be allowed to change again. So we come up with this notion of a stability. We're going to have a window of stability around the falling edge. So D can do anything it wants, and then at some point it has to become stable, and at some point G can change, and then later on D can start changing again here. We have this region of stability, and the time before the falling edge of the gate signal is called the setup time, and the time of stability after the falling edge of the signal is called the hold time. Okay, so setup and hold. So in addition to TPD, for these memory circuits, we have 2 other specifications. Okay, setup time and hold time. And we'll discover that as we'll see when we start using these circuits, in larger circuits, using latches and in larger circuits, that will be very important for us when we're doing the engineering of those circuits. We'll have to make sure that the input to these latches aren't changing, too close to when we're going into memory mode, in order for the memory to be reliably set without any possibility of corrupting the value we're trying to remember. Yes?
But then by the same token, why does T fold only have to be TPD and not another T?
Because once G is 0, once that's propagated through the circuit, now the Q output reflects the fact that G is 0, which means our positive feedback loop is in place stably, reliably. We don't have to wait again. So before we had both the D to output and then Q prime to output. That's what was the two-pass thing. Here we only have a single pass of G through the circuit, and now we're all set. Now we're in positive feedback mode. Okay, so this is called the dynamic discipline. So in addition to the static discipline, we also have the dynamic discipline. And those two rules about the timing of your circuit is what controls the engineering. That's, as we'll see, that's what makes the your processor, a gigahertz processor instead of a 2 gigahertz processor. We had to leave enough time for these timing constraints to be true. Let's try it out. Okay, we're going to put this neat little latch in here. We're going to say, okay, let's use this new device, our new memory device. And when we want it to change from the current state to the next state that we've carefully computed here, I know, let's just put a 1, open up the gate, and let that new value through. But now we have a small problem. If we leave the gate open too long, what will happen? Well, the new state will become the output, the so-called current state. It'll zip through the cycle, and we've basically built ourselves a big loop here. A big cycle. And so this thing will sort of wildly spin away, again and again. So we've got to start on a memory device. The trouble is, in the exact configuration that we wanted to use it, we have this sort of notion of, I want to open up the gate long enough to let something through, but not long enough for it to propagate through the circuit and come back to my input again. So we go, whoop. Was that quick enough? I don't know. So as the little guy here says, this is... We're sort of on the right track, but this sort of tricky business of opening the latch for just long enough to let a new value through, but not long enough for that new value to affect our input because of the cycle. So we're going to say, well, not quite there yet, Chris.